Hello, good morning, everyone. My name is Mark Sims, and we will be talking about quantum computing. We'll be talking about the introduction to quantum mechanics, data representation, computational complexity, implementation technologies, and quantum computer languages. So the introduction to quantum mechanics. Quantum mechanics is a fundamental branch of theoretical physics with wide applications in experimental physics, that replaces classical mechanics and classical electromagnetism in subatomic levels. It provides accurate and precise descriptions for many phenomena that these classical theories simply cannot explain on the atomic and subatomic level. So what is a quantum computer? So can anyone tell me a brief description of what a quantum computer is? Or does anyone know from what y'all are reading right here? No one? Okay. Well, it's pretty much a powerful computer that uses particles that help speed up the processing power pretty much. So it's pretty much faster than a normal 64-bit computer that you have at home or anywhere else. So why bother with quantum computation? So I have a graph here that shows and explains why should we. Moore's law, I'm not going to get into that because it's just a headache, but it says that we hit the quantum level around 2010 through 2020, which you can see right up there how far and how powerful it actually is. Physics and computation. Information is stored in a physical medium and manipulated by physical process. The laws of physics dictate the capabilities of any information processing devices. Designs of classical computers are implicitly based in the classical framework for physics. Classical physics is known to be wrong or incomplete and has been replaced by a more powerful framework, quantum mechanics. So I have a quote that I found by Richard Feynman. He's pretty much saying that it's super complex and super complicated that no one will ever understand how it works. Representation of data. Quantum computers, which have not been built yet, but my guess would have to be probably in the upcoming years of like 2025 or almost 2030, would be based on the strange principles of quantum mechanics in which the smallest particles of light and matter can be in different places at the same time, meaning it's so powerful that zeros and ones can be at the same time. In a quantum computer, 1 qubit quantum bit could be both 0 and 1 at the same time. So with 3 qubits of data, a quantum computer could store all 8 combinations of zeros and ones simultaneously. That means a 3 qubit quantum computer could calculate 8 times faster than a 3-bit digital computer. Typical personal computer today calculate 64 bits of data at a time. A quantum computer with 64 qubits would be 2 to the 64th power faster, or about 18 billion times faster. No, billion 2 times is correct. So that's how fast a quantum computer is. Qubits. A bit of data is represented by a single atom that is on one of 2 states, denoted by 0 and 1. A single bit of this is known as a qubit. As you can see in the picture, the 0 is represented on the top, and the 1 is on the bottom. But let me go back. A superposition can be represented anywhere on a sphere. So like, it doesn't matter anywhere on the sphere, it can be 0s or 1s. Representation of data. A physical implementation of a qubit could use the 2 energy levels of an atom, an excited state representing 1 and a ground state representing what I was just talking about right there. Representation of data superposition. A single qubit can be forced into a superposition of the 2 states denoted by the addition of the state vectors. Where A1 and A2 are complex numbers, A1 and 2 equals 1. A qubit in a superposition is in both of the states, 1 and 0 at the same time. Data retrieval. And generally, an n-qubit register can represent the numbers 0 through 2 and -1 simultaneously. Sound too good to be true? What do y'all think? If we attempt to retrieve the values represented within a superposition, the superposition randomly collapses to represent just one of the original values. Relationships among data entanglement. Entanglement is the ability of quantum systems to exhibit correlations between states with a superposition. Imagine 2 qubits each in the state 0 plus 1. A superposition of the 0 and 1, we can entangle the 2 qubits such as the measurement of the other qubit. Quantum mechanics and information. Any physical medium capable of representing 0 and 1 is in principle capable of storing any linear combination. How does this affect computation and complexity? How does this affect information security? What does efficient mean? The complexity of an algorithm measures how much of some resource, time, space, energy, the algorithm uses it as a function of the input size. The best known algorithms for factoring an n-bit number uses time. Factoring is believed to be hard on a Turing machine or any equivalent model, but how do we know that there isn't some novel architecture on which it is easy? Which crypto systems are threatened by quantum computers? Information security protocols must be studied in the context of quantum information processing. The following crypto systems are insecure against such quantum attacks: RSA factoring, Rabin factoring, Algorithmal, I think, that's how you pronounce it? I could be wrong, but discrete log, including UCC and others. We need to worry now about information that needs to remain private for long periods of time. It takes a long time to change an infrastructure, which I do believe that. Quantum information security. We can exploit the eavesdropper detection that is intrinsic to quantum systems in order to derive new unconditionally secure information security protocols, which have a list right there that y'all see. And I have a photo video here.
If you're among a group of people who either are really into quantum physics or people who have used a computer, there's some big news this week. It took place on a very small scale. Researchers at the University of New South Wales in Sydney have just created a kind of quantum logic circuit out of silicon, but in a way for actual, we're not just talking about them anymore, we could actually build one now quantum computer. Quantum computers are exciting because they're very algorithmic. This won't make browsing the internet any faster, but it will, for example, let drug companies test all of the possible outcomes of different combinations at the same time, which would make discovering new drug treatments is that possible? Well, if you've ever heard of Dr. Schrodinger's Spitz thought experiment, the same logic that applies to the cat applies here. In conventional computers, bits are encoded by circuits that are either on or off, 1 or 0, by using an electrical current, which is the flow of electrons. But quantum computers could use quantum bits, called qubits, by using a single electron. And unlike a digital circuit, an electron can be doing all sorts of things at once. A single electron, for example, might either be spinning in alignment with the nearest magnetic field or spinning perpendicular to it. But until you measure the electron, it's actually doing both at the same time. It doesn't have a defined state. This is called quantum superposition. Now, you still have to measure the spin to get a value for that qubit, so you're still going to get a 1 or a 0. But by measuring it in parallel, you can get multiple values for a single qubit at the same time. So with 2 qubits wired together, you can get 4 values, and if you have 3 qubits, you can have 8, and so on. But guess what? Making actual circuits with qubits is incredibly hard. What the New South Wales team managed to do is boil down all of these ideas to create a quantum logic gate, 2 qubits that can interact with each other. Logic gates are the basis of any digital circuit. They take data from bits, apply programmed logic, the information, and then output the data based on the results. The team took the existing technology in a silicon microchip and reinvented its transistor, the tiny switch that turns off and on to create ones and zeros. So instead of being controlled by a current or a flow of electrons, each transistor basically tracked a single electron and stored its spins as information. They then used microwaves and electrodes in the chip to change the spin of one electron, and therefore the information in that qubit. That information then changed the state of the qubit that it was connected to. The result was a sort of quantum if-then command, where the state of one qubit depended on the state of the other. The researchers have worked out how to scale up this design from 2 qubits to hundreds or potentially millions. And they've patented this design based on the same technologies that are used to make microchips today. So, quantum physics is weird, but quantum computing would be amazing. Thank you for watching this SciShow News, brought to you by Audible, which is giving away a free audiobook to SciShow viewers. Check out audible.com/SciShow, where you can download books like The Pleasure.
So like I was saying before, in the nearest future, so there could be a quantum computer. As you've seen in the video, how they demonstrated that, how that helped understanding my nonsense of what I went through and saying. But before they invented that, they had no way of finding out what were zeros and ones. They weren't able to figure out how a quantum computer worked. And so I hope that helped. Thank you.